In the last video, we talked about how pressure can affect boiling points, but pressure can also affect melting and freezing. So I want to start by just kind of giving you the words that describe what happens. And it turns out that for freezing and melting, I have to give you two sets of information. So first is just most substances. And it will be just about everything. The second set is going to be for water, and then there are some other things that have the same properties as water that might follow this. So for most substances, what you tend to know about how phases work applies. So the solid phase is more tightly packed than the liquid phase. And by more tightly packed, we mean more dense. So if you have this solid substance and you increase the pressure, that pressure helps hold the molecules together. So high pressure helps hold. So if you wanted to melt this, you would not only have to overcome the intermolecular forces, you would also have to overcome the pressure that is trying to push these molecules together. So at higher pressure, you need a higher temperature to melt. Unlike most substances, in water, which we have brought this up already, and this is something that you know from just observation, the solid phase is less dense than the liquid phase. This is why ice floats. This is how fish survive in frozen over lakes in the winter, because all of the ice forms on the top so they can still be in the water underneath. So if you had a solid piece of ice and you applied a high pressure to it, it would push those molecules closer together and it would help melt it. So increased pressure pushes molecules together and helps with melting. So at higher pressure, a lower temperature is needed to melt it. So at increased pressure, decreased temperature needed to melt. All right. So this is a lot of information. It's not really something that I want you to memorize, because we have this really great thing called a phase diagram that's just a picture that tells you all of this information. So you will be able to look at a phase diagram and figure out if at high pressure you need a higher or a lower temperature in order for something to melt. So I promised you a picture, but I am going to give you a bunch of words to describe what's going on in a phase diagram, and then we're going to look at two examples so that you can see what each type would look like. So phase diagrams. They are a plot of pressure versus temperature. So you'll have pressure on the y-axis, temperature on the x-axis. That essentially results in a map. Showing which phase is most stable at each pressure and temperature combination. So you will see a couple of lines, and then you'll see a bunch of open areas in this phase diagram. So the lines are called phase boundaries. And this line represents the pressure and temperature at which the phases are in equilibrium. So, for example, on the liquid vapor line, which sometimes you'll see the gas phase listed as the vapor phase, sometimes you'll see it listed as gas. I'm fine with you using either. I just want you to know what you might see when you go look at phase diagrams. So the liquid vapor or the liquid gas line, it can give you the vapor pressure at any temperature. So if, for example, we were thinking about a temperature of something below the boiling point, if you went up to the liquid vapor line, the pressure that you read would be the vapor pressure. So if you follow that vapor pressure, say up to 1 atmosphere, it should correspond to a point that matches the normal boiling point, because the normal boiling point happens at 1 atmosphere. Or you could use this line to tell you the boiling temperature at any external pressure. So the pressure that you read, if it's anything other than 1 atmosphere, when you are at that pressure, the corresponding temperature is the temperature at which that liquid would boil. All right. You will also see a solid vapor line. So this will give the vapor pressure of the solid at any temperature, which we have not used solid vapor pressures for very much, but solids can have vapor pressures. Or, right, we have talked about sublimation. So sublimation is going directly from a solid to a gas without passing through the liquid phase. So this will give you the temperature at which something sublimes at any external pressure. All right, so liquid gas, solid liquid. Gives the melting freezing temperature. We'll say melting / freezing temp as a function of P external. So all of the words that we just said about how pressure affects melting, we will see those effects in the solid liquid line. So what we are going to find is that you'll be able to read this just like any other graph. So following the pressure, following the temperature. So if something melts at a higher temperature, at a higher pressure, so this is going to be our most substances, this line, I'll put this in quotes, but we'll see it in the picture in a second, leans to the right. because as the pressure and the temperature goes up, they have a direct correlation. And then water and others with similar properties, which usually just means hydrogen bonding. This line leans to the left. On a phase diagram, there's also going to be two special points that you will see. So I'm going to define those for you, and then I promise we'll actually draw a picture. So 2 points. And one is going to be the intersection of those phase boundary lines that we talked about, and then the other one is just going to be the end of the line on one of them. So there is something called a triple point. So this is where all three lines intersect, and it will be the point at which all three phases are in equilibrium. So if you had a container that was at the pressure and the temperature of the triple point, you would have solid, liquid, and gas, all of it in equilibrium together. If you go below the pressure of the triple point, the liquid cannot exist. The other point that you will see is something called the critical point. And so at the critical point, the pressure and temperature are so high that we actually get a new phase. So we won't have a solid or a liquid or a gas. What you have is there is high density vapor and low density liquid. And they become one state. And we call that state a supercritical fluid. So above the critical temperature, the liquid phase cannot exist. So this supercritical fluid is actually used widely in manufacturing, and it's really cool because it has the properties of a liquid and the properties of a gas. So in the past, to do something like make decaffeinated coffee, they would pour dichloromethane on coffee beans. And it would dissolve the caffeine, and they would wash it away, and then they would try to evaporate the rest of the dichloromethane out of the now decaffeinated coffee, which is quite terrible, to be honest, because dichloromethane is very carcinogenic. It doesn't go away completely, so it also makes your coffee taste bad. So getting away from using that is very useful. So they use supercritical carbon dioxide to make decaffeinated coffee now. Supercritical CO2. So you can basically dissolve the caffeine in the liquid carbon dioxide when it's acting like a liquid, get it washed away, and then the carbon dioxide just evaporates. I have also heard, I think it's supercritical CO2, but it might be a different substance. You can use supercritical fluids to do things like dye extractions or dyeing fabrics, because then you don't have any solvents left over that are generally really bad for the environment. Okay, so 2 pictures of phase diagrams. First, I'm going to give you the phase diagram for water. So like I said, it's going to be a plot of pressure versus temperature. And what I'm going to do is get some points on here, and then I will come back and fill them in. So now that I have the points on here, I'm going to add some lines, and then we'll get the sections labeled. So I have one line that is going to come through here. And then one more that comes this way. And if I label these C, A, D, B, maybe not the best order, but we can talk about what each of these points are and what each section is. So this section to the left is solid, so under any pressure and temperature conditions that are contained between those boundary lines, you would have a solid present for whatever substance it is, in this case water. This is the liquid section up here in the middle, and then everything down here is a gas or a vapor. So that means that this line that I'm going to highlight in orange, this is my solid vapor line up until orange. In blue, right, it's the boundary between liquid and vapor, so this is my liquid vapor line. And we'll go pink because it shows up differently. This boundary between solid and liquid is my solid liquid boundary line. Okay, so in terms of identifying what each of these points are, point A, where everything comes together, right around point A, you can see all 3 phases. This is the triple point. Point B, it's high temperature, high pressure. And if you look in a lot of phase diagrams, you'll kind of see this dashed set of lines that go at 90 degrees out from this point. That's the critical point. And so in this section is actually where you have supercritical fluid. So B is the critical point. Points C and D, I think you would be able to figure out based on how I've labeled, but let's look at them explicitly anyway. If I take a dashed line across this pressure reading, that's at 1 atmosphere. And if I go down from point C, this is 0 degrees. So at 1 atmosphere, this is the freezing point. This is my normal freezing point. At point D, it's at 1 atmosphere. If I check that on the x-axis, that's 100 degrees. This is my normal boiling point. So this is the phase diagram for water. And remember, the thing that we were looking for that tells us about the density of the solid compared to the liquid and how the melting point is affected by the pressure, it's the line that I've highlighted in pink. It is the solid liquid line, and it leans to the left, right? So if we're looking from A through C going in this direction, right, my line leans to the left. Now, if it doesn't feel like it leans to the left to you, what we're looking at is that my normal freezing point at 1 atmosphere is 0 degrees. If I were to go up to some higher pressure value, and this doesn't have a good label, and pick my solid liquid line point and carry it down, my new freezing point is lower. So my freezing melting point. So my solid would turn into a liquid at a lower temperature if the pressure is higher. That's the main piece that we're looking for. Okay, so as a contrasting example, let's do a phase diagram for carbon dioxide. So it's still just a phase diagram. So we're going to do pressure versus temperature. And this one, it's going to be just a little bit different in terms of the scale. So what I'm going to do, like I did before, is pause really quickly, get some points on there, even though when you're watching this, the points will already be there, and then we'll come back and fill in the lines. So in the CO2 diagram, the pressure ranges that we're looking at go up to 73 atmospheres. And then in terms of temperature, we're going from below minus 78 and then up to 31. So the lines on here go through and continue up. Sorry, that's a little bit wobbly. And then out of here, I have this line. So I still have solid in this section to the left, liquid in this middle part, and gas or vapor down here. So in terms of labeling the points that I have, I've only got 3 marked on here, but some of them you'll be able to see. So like point A, right, this looks like it has 3 phases in equilibrium. Point A is the triple point. Point B is the end of that liquid vapor line. So point B is the critical point. And then point C, this is different from what we've seen before. But if we look, it's at 1 atmosphere. It just happens to be on the solid vapor line. So that equilibrium between solid and vapor is sublimation. So at 1 atmosphere, it's the normal sublimation point. Now, if we were to carry this 1 atmosphere all the way over, it doesn't intersect with anything else on our picture. So that is the only normal phase change that exists for CO2. We could obviously have other phase changes. They would just not be considered normal. So you could have a boiling point. It just wouldn't be a normal boiling point because it would be at a pressure other than 1 atmosphere.